So our next topic, we're getting into a thing called colligative properties, okay? And a colligative property, let's switch to a new topic, a new color. And colligative properties are certain types of properties that don't depend on the identity of particles, only on the number of particles. Okay, and we're talking about mixtures. So solutions. So if I have sodium chloride dissolved in water versus magnesium chloride dissolved in water, doesn't matter which is which. It just depends on how many particles of sodium chloride or magnesium chloride there are. Okay? Doesn't matter whether it's sodium or magnesium. A colligative property only depends on how many particles there are. Okay, so the first one that we're going to talk about, and you guys get to do a lab about this one, is osmotic pressure. Okay, and the reason what's interesting about osmotic pressure is it has to do with water, okay, primarily. But it can be about other liquids and other mixtures. But osmotic pressure is defined kind of oddly. Osmotic pressure is defined as the pressure needed to stop osmotic flow. Okay? And osmotic flow is a natural tendency to increase entropy, just like mixing. Okay, so let's talk about an example of what this is. So imagine that I have a container, and it's separated down the middle by a semi-permeable barrier. Okay, so I've got this container here, and running down the middle, I have some sort of barrier that is semi-permeable. Okay, so meaning that water molecules can pass through the barrier, but solvent particles cannot. Okay, and on one side of the barrier, I set up with 1 molar sodium chloride solution, some salt solution. Okay, and on the other side, I have just pure H2O. Okay, so what's going to happen is that water will move. So the H2O is going to pass through the barrier to the sodium chloride side. And given some time, what this is going to look like, imagining that my walls are flexible, is that on one side I will have all of the water, well, not all of the water, but some of the water. But we'll be dealing with, on the left side now, I have significantly less than 1 molar sodium chloride solution and much less pure water over here. Okay? Why does it do this? Entropy. Entropy drives the flow of water from one side to the other. Okay? What it does is by decreasing the concentration of sodium chloride, results in more microstates. Okay? So I have the same number of molecules of sodium chloride on the left-hand side. But if I flood that with a whole bunch more water, Now those same number of sodium chloride molecules have more places they can go. They can go farther, they can go in different directions, they can go in different speeds. By diluting the sodium chloride, I'm actually increasing the entropy. And this is why water will flow flow into areas of high concentration. Okay. So on the right-hand side of our container here, we have pure water. On the left-hand side, I have water mixed with some stuff, so significantly higher concentration of sodium chloride on the left. So the water will flow toward the area of high concentration in order to dilute that thing. Okay. So our symbol for osmotic pressure is capital Pi. Okay. Capital Pi is the symbol for osmotic pressure. Okay? And at a certain point, the water is going to keep flowing, and at a certain point, it's going to stop flowing. And at which point, we have reached the osmotic pressure, the pressure needed to stop the flow, the osmotic flow. Okay? So the symbol for pi, for osmotic pressure, is capital Pi. Right? And it's related to the ideal gas law. Okay, which is kind of fun because we dealt with the ideal gas law in Gen Chem 1. So pressure times volume equals moles times the gas constant times temperature. Okay, and this is the standard 0.08206 liters atmospheres over moles Kelvin. Okay, so I can rearrange this thing and put osmotic pressure all by itself. So pi equals nRT over V. And guess what? Molarity is moles over volume. Okay? So in the end, our equation equals molarity times RT. Now, let's take and do an example problem using osmotic pressure. So let's find molar mass from osmotic pressure. Okay, so we are looking for grams per mole. All right, so first we're going to dissolve some unknown in a solvent. Let's say that we're going to dissolve 1.08 grams of albumin, so protein. Okay, but we don't know if it's bovine albumin or human albumin or some other kind of thing. We want to determine what is the molar mass of this albumin. Right? So we dissolve the unknown in the solvent and we measure the osmotic pressure. And we find that the osmotic pressure is 5.85 millimeters of mercury, which equals 7.70 times 10 to the minus 3 atmospheres. Okay. So we already know mass. We know that we have 1.08 grams of albumin. So we need to find moles. Okay, or in this case, N. Right? So N equals pi times V over RT. All right. And to be completely frankly honest, I forgot to include the temperature in this particular problem, but suffice to say that the temperature is such that we end up with an answer for N of 6.87 times 10 to the 4. Nope, wait, sorry, that's the final answer. Getting ahead of myself here in my notes. 1.57 times 10 to the minus 5 moles. Okay, so molar mass is grams per mole. So we end up with the 6.87 times 10 to the 4. Rather large molecule. Okay, so other colligative properties that we're going to deal with. So that osmotic pressure was just the first. There are several colligative properties. So the next ones to deal with are freezing point reduction and boiling point elevation. And boiling point elevation. Okay, and we're talking about of solutions. Okay, versus pure solvents. Okay, so if we're talking about making a mixture in water, water freezes, pure water freezes at 0 degrees Celsius. But if I make a solution, dissolve something in that water, now it requires me to drop the temperature further, freezing point reduction. So the freezing point will go down further than 0. So maybe it freezes at -1 or -2 or -6 or -15. Right? Conversely, water boils at 100 degrees Celsius, and if I add some solute to the water, now the water is not going to boil until it gets to 102 or 105 or 106 or higher. Okay? So, and the point is that this is a colligative property, or these are colligative properties. So the number of particles that I add to my solution will push the boiling point further down or push the freezing point further down or raise the boiling point higher up. Okay? And we have equations for it. So the ideal form, and we'll talk about the real form later, a little bit later on, but the ideal form for these equations is that the change in the freezing temperature is equal to negative Kf, which is a constant for a particular solvent, times molality. Different from molarity, molality. Okay? And molality is, if you're not familiar, is lowercase m. Okay? And our delta Tb, change in boiling temperature, is equal to Kb times molality. Okay? So keeping in mind that these are constants for a particular solvent. Okay? And molality is moles of solute per kilogram of solvent. Okay, different from molarity. Remember, molarity is moles of solute per liter of solution. All right? Molality separates the two, moles of solute versus kilograms of solvent. Okay? And to clarify our delta TF and delta TB, if I'm talking about the delta TF, we're talking about the temperature for the normal solvent, freezing point, minus the new temperature. Okay, so let's annotate that so you have it written down. Normal freeze temp for pure solvent versus the new TF for the mixture. Okay. All right, so let's do an example problem. Actually, a couple of them. So here is our question. I'm going to write it out by hand, just like I would in class. So seawater contains 3.4 grams of salt for every liter of solution. Assuming the solute is primarily sodium chloride, calculate the osmotic pressure of seawater. At 20 degrees Celsius, sorry. Okay, so we have a couple of forms for our osmotic pressure equation, right? So we have pi equals nRT over V, which also equals molarity times RT, right? So our molarity is 34 grams per liter, right? But we need that in moles per liter, right? Our concentration is 34 grams per liter. So let's convert that to molarity. So we have 3.4 grams of sodium chloride per liter. Convert to moles. Sodium chloride is 57.44 grams per mole. So we have a molarity of 0.05919. Keeping track of sig figs, we're going to track at 2 significant digits. And yes, folks that are watching at home, sig figs still count. Okay, so now that I know the molarity, all I have to do is plug in the values, making sure that I use temperature in kelvins, because that's the units of R. Our molarity of the salt water solution times the ideal gas constant, 206 liters atmospheres over moles Kelvin, times 293 Kelvin, means that our osmotic pressure of seawater is 1.4 atmospheres. Right, so next question, we're going to employ our other colligative properties for this problem. So let's calculate the boiling point and freezing point of a solution of ethylene glycol in water. Okay, basically antifreeze. And we're specifically dealing with a 25% by mass. Solution of ethylene glycol. And ethylene glycol has a formula C2H6O2. Okay, so in order to do this, we need a couple of things, and you'll be supplied with the Kb and Kf values for water. All right, so Kb for water is 0.51 degrees Celsius per molal, and Kf is 1.86 degrees Celsius per molal. Okay, so it should be hopefully glaringly obvious at this point in time, the piece that we're missing is the molality. Okay, so let's switch colors so it's easier to see our work. So a 25% by mass solution is the same thing as saying, if we assume 1,000-gram solution, it's the same thing as saying 250 grams and 750 grams of H2O. Because if our solution weighs 1,000 grams, 25% of that will be the ethylene glycol and the rest will be water. Okay? So that's how we arrived at the 250 and the 750. Okay? But molality is moles per kilogram of solvent. Moles of solute per kilogram of solute. Gosh, it's easy to get those words confused. Moles of solute over kilograms of solvent. Okay, so let's use these values and convert them into molality for ourselves. Okay, so we have 250 grams of the ethylene glycol per 750 grams of H2O. All right, so let's convert to moles of ethylene glycol. And that's 62.1 grams. Okay, so if I stopped here, I would have moles per 750 grams of water. So I need to convert those grams into kilograms. Okay. So if I'm careful with my writing all my units down, which I encourage you to do so, grams of ethylene glycol go away, grams of water go away, leaving us with moles per kilogram. So we end up with a molality of 5.37 molal. Okay, so let's plug these things in. Okay, so our change in boiling point, our delta TB equals Kb times molality, right? So that's, the Kb was 0.51 degrees C per molal times 5.37 molal gives us a boiling point elevation of 2.7 degrees C. Okay, now it's important to realize that 2.7 is not the new boiling point. Okay, let me write that down in a nice bright color. Not the new boiling point. Okay, this is a change in boiling point. So boiling point elevation. So the normal boiling point plus 2.7. Okay. So let's find our change in freezing point now. So delta T freeze is negative K freeze times molality. And that's the 1.86 degrees Celsius per molal times 5.37 molal gives us a depression of minus 10 degrees Celsius. I wrote that right, didn't I? Yeah, okay. Okay, so again, that minus 10 degrees C, that's not the new freezing point. That is the change in the freezing point, okay? It's very easy to say, ha, I have the answer, minus 10. Well, if you're dealing with water, sure, because water freezes at 0, right? But, so we want to take a look at our, what are the actual new temperatures? So you'll have to forgive me, this particular, finding the original or the new freezing point and boiling point is something that always twists my brain a little bit in trying to explain it to others. So I'm going to write these equations, and these are the ones that I want you to write down clearly. So the delta TB, okay, anytime you're dealing with delta, it's final minus initial. So our final is our new boiling point. So TB minus our T initial, which is our original boiling point, okay? So delta TB plus T initial equals our new boiling point. Okay, so water boils at 100 degrees C, so our delta TB is 2.7 degrees C plus 100 degrees C. So our new boiling point is 102.7 degrees C. Okay. Now our delta TF, same thing. It's supposed to be final minus initial. So delta TF, and this is what I want you to write down, is the new freezing point minus the original freezing point. Okay. So TF, our new freezing point, equals delta TF plus T initial, okay? In this case, our original freezing point for water is 0 degrees Celsius. So we have minus 10 plus 0 equals minus 10. Okay? I do apologize for any confusion, but these equations in blue, these are the ones that I want you to keep in your notes, okay? I want to make that very clear. Keep these in your notes. Okay, so let's twist this around a little bit and do another example problem, okay? Where we can use these equations to determine concentration, okay? So here's our example. We're going to add some solute to H2O. Measure delta T and determine the concentration of particles. Okay. So TF normal for water is 0 degrees Celsius. Okay. For H2O liquid. Water freezes at 0 degrees. Okay. If our delta TF equals negative 1.94 degrees C. And Kf, our constant for water, is the 1.86 degrees C per molal. Okay. We can solve for the molality. So delta Tf equals negative Kf times molality. Right? So molality, if we rearrange, equals delta Tf divided by negative Kf. 1.94 degrees C divided by negative 1.86 degrees C per molal equals 1.04 molal. Okay? But we want to know concentration. Okay, so molality is a version, so let's find what it is in molarity. So molarity of particles. So right now we have 1.04 moles in 1 kilogram of water. Right? And water has a 1 gram per milliliter density. So 1 kilogram of water also equals 1 liter of water. Okay? So if I just take my molality and do a little one-to-one conversion, means that I also have 1.04 molar particles, molarity. Okay, so we can use these equations in a number of ways. We can solve for concentration if we know delta T. We can even use molality and delta T to find the constant in many cases. Okay. So in the process of determining a lot of these K values, scientists found that there were situations that didn't quite match up with what they expected. Okay, so let's look at a couple of examples of how to deal with that and what that sort of means. So experimental evidence, let's say we're talking about some acetic acid. So if I put some acetic acid in water, so CH3COOH, let's say it's 0.01 molal in H2O. The predicted delta TF should be negative 1.86 C per molal times 0.01 molal. It's just negative 0.0186 degrees C. So it doesn't really affect our freezing point very much. And the actual, when they did this experimentally, also equaled the same. Great, cool. Right? Well, let's look at a different scenario. For the same molality of lead nitrate, for example, instead of something simple like acetone, or acetic acid, excuse me, NO3, 2, right? The predicted delta TF should be the same as for the acetic acid. But what they found out experimentally, the actual delta TF was negative 0.0489. Okay, so what? All right, so if everything is working perfectly and everything's ideal, then we should get the same for the lead nitrate as for the acetic acid. But experimentally, that wasn't the case. So scientists said, well, is it ionization? Right? So in this concentration of lead nitrate, we have 3 moles of ions per molecule, right? Right, so let's assume that's true, and that gives us a concentration of ions of 0.3 molar ions. Right, so if we plug that in and solve, we get an answer of negative 0.0558 degrees C. That's too much. Okay, so just making the assumption that this thing breaks apart perfectly into all of its ions also doesn't account for the experimental evidence. So what we have is a new concept called the Hoff Factor. Okay, and it has the symbol lowercase I. All right, and what the Hoff factor is actually a fractional multiplier for our freezing point depression for any of our colligative properties, really. Okay, and how we figure out I, we have to know the actual and the predicted delta T. So I equals the actual delta T divided by the predicted delta T. Okay, so in our case, with the lead nitrate, our actual was negative 0.0489, and our predicted originally was 0.0186. So we get a Hoff factor of 2.63. Okay, and this is for this concentration of lead nitrate. Okay, so what the Hoff factor really is the effective number of particles in solution. So we found when we just assumed perfect ionization, we should have gotten exactly three times the number of particles. But when we put that into the equation, it didn't come out right. So the Hoff factor is the effective number of particles. It's not exactly 3. Okay, so why not? Okay, in real solutions, ions attract. So the question is, why is I less than 3? And in real solution, ions attract each other. Okay, so ideally, if we have an ideal, in other words, a very dilute solution, right? I've got some nitrate ions. See, I've got 2 of those for every lead ion, right? So, and they separate perfectly and everything goes just fine, okay? We have 3 ions for every 1 solute molecule, right? So in But in more concentrated solutions, the ions clump some. Okay, so instead of having a perfectly sort of, thrown apart sort of thing, I've got some leads and I don't know why that one was, and some nitrates, but I also have a lead and a single nitrate with a plus sign, right? Or I've got a pair of nitrates or a pair of leads stuck together. Okay, this clumping happens, right? And the effective number of particles ends up being less than the perfect 3 per molecule. Okay, less than the 3-to-1 ratio. So the Van Hoff factor actually goes into each one of our colligative property equations. Right? So I said the ideal equations. Now I'm going to give you the true equations. And I said the Van Hoff factor is a multiplier. So for each one of these, we just simply plug in the Van Hoff factor into our equation. So osmotic pressure equals I times nRT over V. And delta TF equals negative KF times I times molality. And delta TB, same thing. KB times I times molality. Right? So I makes things more accurate. Now, a lot of times you can assume ideal behavior. Okay? You will generally be told you need to find the Van Hoff factor. Okay? And if you have to find the Van Hoff factor, you have to be given the experimental change in the colligative property. Okay? So you're not expected to conjure a Van Hoff factor out of thin air. You have to know what the experimental, the actual change is. Okay? So let's think about certain types of molecules and how their Van Hoff factors might play out. So if I have something like sodium chloride, it's ionic, it's soluble in water, right? That means that I'm probably going to get around 2 ions per molecule, right? So I can have probably have an Van Hoff factor somewhere around 2, right? But let's think about something like a protein, right? Some sort of, or better yet, let's revisit our friend hexane. Right? So hexane, nonpolar, right? Not soluble in water, or not miscible. Okay? So it's not going to mix. So we're going to actually have a Van Hoff factor of 0. Okay? But let's think about something like a soluble protein. Okay? Will mix, but doesn't come apart. We'll have a Van Hoff factor of 1. Okay, so we really only have to worry about mixtures that involve ionic compounds that will come apart into more than one piece. Okay, so sugars, proteins, soluble molecules, things of that nature are all going to have Van Hoff factors of 1, right? But soluble ionic compounds that come apart into more than one piece, you may have to deal with a Van Hoff factor, in which case you'll be given the change in the freezing point, boiling point, or the osmotic pressure, the actual experimental values. Okay, so this ends your chapter 13 lecture. Hopefully it is not too confusing. If it is, please let me know. Ask questions, join a Zoom, get on the chat, all that good stuff. So have fun, and I'll talk to you all soon.